Hi everyone, my name is Sergey Levin, and today I'm going to talk about how robots can learn end-to-end from data. Let's start with a thought experiment. Let's imagine that it's the year, for example, 2030, and you just bought a brand new home robot. It's a general purpose robot that is supposed to do all sorts of chores around the house. You could imagine it looks like this, or maybe like this if you're more inclined towards classic cartoons. And today what you're going to ask the robot to do is to clean your bathroom. Now maybe you live in a small cramped apartment, maybe it's not the easiest bathroom to clean, but you give that robot the task and you go to work. And it doesn't do a very good job, so while you're away at work, the robot tries to clean it up. That funny looking sink in the corner gives it a little bit of trouble. Maybe it even spills some water on the floor. Maybe it doesn't realize the bucket for the water has a broken handle or something like that. So when you come home, okay, it did its best. The bathroom is only a little bit cleaner than when it started, and there's some water in the corner. The next day, it tries again. It does a little bit better. By the third day, it has gotten a lot better. It has really mastered that task, and it can do it with a kind of robotic precision. And then after that, you're pretty satisfied with it. You can give it that task every time it needs to do it, and it will do it just perfectly. Okay, so what's the point of this thought experiment? The point is to give us a backdrop against which we can frame a lot of the challenges that we need to tackle to make general purpose robots really viable in the real world. Imagine the kinds of technologies that we would need to make all this possible. To have the robot acquire in advance some capability so that it even has a vague sense of what to do in your bathroom, while at the same time having the ability to keep learning and keep improving so that day after day, even if it makes some mistakes, it can recover from them entirely autonomously without your intervention. So even though it messed up and spilled that water on that first day, it still figured out that something had gone wrong and took steps to correct it. Of course, in reality, we care about these things not just because we want home robots that will clean our bathrooms. Robots that can perform complex tasks in open world environments like this will have far-ranging repercussions, and they will likely transform our society in ways that we can't even imagine. But what I would like to focus on in today's talk is the kind of technological challenges that we'll need to overcome to make this possible, and hopefully tell you a little bit about some of the recent work from my lab that perhaps give us a hint of how some of these challenges could be tackled. So here's a recipe that we could imagine that might maybe one day make this kind of thing possible. Let's say that we have a large data set from past interactions, all the things that robots have done before, maybe other robots of that particular brand. We need a large data set because in order for that robot to have even a vague sense of what to do in your bathroom as soon as you unpack it from its box, it needs to have already learned a lot from large repertoires of prior data. Large repertoires of data are the only way that we know right now to learn generalizable concepts. That's what has succeeded time and again in computer vision, speech recognition, and NLP. So we'll need something like that. We'll need essentially a basis of understanding from which the robot can build up its skills. So this prior data set will be used to train the best possible initial model that the robot can use to go out onto the world. But of course, that can't possibly be perfect. So initially, it will attempt the task to the best of its ability in your bathroom, and it will spill water all over the floor. So that's where the next part comes in. It has to fine-tune from this additional interaction in the particular environment where it's deployed, and crucially, it needs to do this autonomously. If the robot relies on you to go in and fix things up and allow it to try the task again, you'll of course never want to deal with it. But if it can do it while you're away at work, if it can try to clean up the spill, in the process learn a little bit more about how things work in this novel environment and get better and better, then it might actually be a viable practical system. So some of the things we might need. We might need to be able to use large amounts of prior data for offline training. Essentially, the robot needs to take all the data collected before, maybe by all the other robots of that type, and use it to learn the best policy available for, let's say, the task of cleaning a bathroom. And this is a general kind of category level task, cleaning any bathroom. And then once it's deployed in your particular environment, it needs to fine-tune that skill using additional experience it gathers. Now that's of course the algorithmic layer. The algorithmic layer is not everything we need in order to have systems like this actually be successful. We also need to think about the practicalities of such a system. It can't be a single task system because a single task system would never be able to perform these tasks autonomously because things will go wrong, unexpected events might happen, and it might need to perform other tasks just in service to the main task it was given. For example, if it spills water on the floor of your bathroom, it needs to switch to cleaning up that spill before it can resume the rest of the bathroom cleaning task. So this kind of autonomous retrying and practicing will be an essential component of allowing these systems to be truly autonomous. And of course, in order for such a system to actually be useful, it can't just be a single task system. It needs to be able to do many of the things that you might want. It needs to be a general purpose system, which means that we need scalable algorithms that can master a huge number of tasks, not just individual tasks. At that point, we need to think about how these tasks are defined, how we can remove a lot of the manual burden of task specification, how you communicate goals to the robot, and how you can practice those tasks autonomously. And these are all things that we will need in order to instantiate such a system. We don't know how to do all of them perfectly yet, but what I will tell you about in this talk is some initial steps we've taken to maybe get us closer to that goal. So in particular, I'll talk about three big components that I think will be important for this to work. Reinforcement learning algorithms that can use broad and diverse data sets. So that's the bit where you use large amounts of prior data to get the best possible skill you can. Number two, how you can leverage this starting point to rapidly adapt to new tasks. So this is what happens when the robot is trying to clean your bathroom on the first day and the second day and the third day. And number three, which is maybe less obvious, but in my opinion very important, is how to do all this fully autonomously in real-world settings. And this is actually a fairly deep problem. How do you not only practice the task in the new environment, but actually decide automatically how to do whatever behavior is necessary to enable you to practice the task? When you spill the water, how do you clean up the water? If you lock yourself out of the bathroom, how do you find the key to unlock it again? Whatever you need to do in service to continuing to perform the task without the need for any human intervention. So let's talk a little bit about that first question, scalable robotic learning algorithms. And in this part of the talk, what I'll discuss and hopefully try to convince you of is how we can distill knowledge and common sense from data. But let's start with a little example. Let's say that you would like a robot to cut an onion. Okay? And you're going to use reinforcement learning, so you put a knife in the robot's hand and you have it practice the onion cutting task. And it gets really good at it. Now it really knows how to cut an onion when an onion is placed before it and it's holding a knife. And then you're going to put that robot in someone else's kitchen, and its job will be to go and cut onions. The problem is right off the bat, the robot has no idea what to do. What it learned is when you're holding a knife, how do you move that knife to cut an onion? Now it's not holding a knife anymore and there's no onion in front of it. Any person would probably guess what they should do in this situation. You know, they should go find a knife, they should go find an onion and start cutting. People have common sense. Common sense would allow us to not lose our heads in this situation. Even though we don't know exactly what to do, we can kind of take a rough guess and we can use our mental faculties to do something reasonable. What I'm going to argue is that the way to get this common sense for robotic systems is to use data with appropriate offline RL algorithms. Here's how this would work. The current task, the task of cutting an onion, involves episodes, trials, where the robot is holding a knife and cutting an onion. So initial state is holding knife, final state is onion has been cut. And that's the data the robot has to learn this task. Whether it's learning it with RL or imitation learning, kind of doesn't matter. In the end, if it's using RL, it might not start off with that data, but it would gather that data in the process of reinforcement learning. But now imagine that we also take prior data from a wide variety of other tasks that the robot has done. Tasks that don't involve actually cutting the onion, but maybe it had to take a knife out of a drawer for some other purpose, maybe in order to wash that knife. Maybe it had to take an onion in order to put it into another container. So it's seen drawers, it's seen knives, it's seen onions, just not in the context necessary to actually perform the complete task that you're giving it. Well, a reinforcement learning algorithm that learns a value function should be able to figure out how to stitch this experience together. Essentially, the robot will learn that the state where it's holding a knife is a good state. It's a state that leads to successful completion of the cutting task. And from that, it can generalize and figure out that any state in the prior data where it's holding a knife is also a good state for cutting an onion, because holding the knife is good for cutting the onion. So the state with a knife is a good state, and therefore any state with a knife in the prior data is also a good state. And that means that any state that led to that is also a good state, such as the one where it opened a drawer, saw some knives that it could take out. And by backing up these values into the prior data, it can essentially repurpose this prior data to acquire a notion of common sense. Of course, in reality, not all prior data is useful for this task. Maybe it also has some data of grating cheese into a soup and cutting a carrot and baking bread, but none of that is, of course, useful to the task at hand. And of course, a reasonable offline reinforcement learning algorithm would figure out that this data is not useful. Those states don't have high value. So you don't need to decide that drawer opening and onion grasping are useful for this task. You just have to give it all the data and allow it to back those values up into the prior data set. And this is the essential benefit that we would get from reinforcement learning with broad and diverse data sets. It's not just generalization in the kind of computer vision sense where you can be robust to visual variation. It's generalization in the sense of common sense, in the sense that the robot would be able to use diverse experience to link together different parts of trials that it's seen before to perform tasks in novel situations. So let me tell you about a project we did to investigate whether such a thing is possible. This is work led primarily by my student Abhi Singh called COG, Connecting New Skills to Past Experience with Offline Reinforcement Learning. Now, we didn't do onion cutting, we did something a little different. So let's say that the task is to pick up a ball from a drawer. So the data that you get for practicing this task is where the drawer is open and you just have to pick up the ball. If you just train a policy this way, just like the onion cutting policy would be confused when placed into a new kitchen, this policy would be very confused if you place it in a scene where the drawer is closed. It wouldn't know how to open it. But instead of just giving it this data, we'll also give it a large collection of prior data that illustrates a variety of different behaviors. Some of those behaviors are not useful. They might, for example, involve closing a drawer or moving an object in an irrelevant way, or even just moving the arm about randomly. But some of it might be useful. It might involve, for instance, opening the drawer or moving an obstruction out of the way. And the same basic logic that I discussed before in regard to the onion cutting could be used to link up this data to the task of grasping the ball. So more precisely, the setup is that you have data for your particular tasks and prior data. This is a fully offline training setup, but you could imagine the training data for your current task could also be collected online with regular exploration. So for the current task, you have sparse 0-1 rewards. So you just get a reward of 1 when you've done the task successfully. You have to learn the task from images, and you only see the task from a single starting condition. So for the task of grasping the ball, it is only ever attempted when the drawer is already opened. The prior data has no rewards at all. All rewards are 0. You don't know what is useful for your task and what isn't. And none of the prior data actually accomplishes the task. There's not a single episode of actually grasping the ball in the prior data. But there are many other things like moving and picking up objects, opening drawers, closing drawers, things that could potentially be useful for performing the task at hand in a new setting. The training method is just running offline reinforcement learning. The particular algorithm we use here is conservative Q learning, which was developed by my student Avaral Kumar, which I won't go into in detail, but it's just used off the shelf in this particular setup where you have prior data and very narrow training data for your particular task. And the approach actually works. It actually links up relevant episodes and prior data in the right way. So you can get a policy that picks up the ball from the open drawer, and without ever having seen drawer opening and picking in combination, only having seen those separately, as soon as you place it in an environment where the drawer is closed, the policy actually already knows that it should open it and pick it up. So the policy has a degree of common sense. If the top drawer is open, it will first close the top drawer, then open the bottom drawer, and then pick up the ball. And if there's an obstruction in the way, it'll pick up that obstruction, put it away, then open the bottom drawer, and then pick up the ball. So it can chain multiple behaviors together like this, and it exhibits a degree of common sense that is distilled entirely from that prior data. And this is why utilizing prior data is so important. All right, in the next part of the talk, I'll talk about a very different application that starts to get at that second point, how we can adapt quickly for a particular new task. I'm going to talk about a robotic delivery driver, specifically learning to navigate from diverse data. And this is work that was led by my student Dhruv Shah in 2 papers, VING, Learning Open World Navigation with Visual Goals, and RECON, Rapid Exploration for Open World Navigation with Latent Goal Models. So what we're going to be concerned with is the problem of getting robots to navigate to user-specified goals. So this is a little vignette of a potential mail delivery application. The idea is that a user takes a photograph of their front door, that's shown by those pictures on the left side, and then the robot navigates to the specified goal, the goal specified with that picture, using entirely onboard camera observations. So there's no GPS, there's no localization, there's no SLAM. This is entirely done with a learned model. A learned model that just takes in onboard images and then navigates to the goal. And I'm going to show you how that works. There's no trickery here. This is actually performing the task entirely from first-person images. This is the kind of thing that usually would require a fairly complex system involving SLAM, localization, planning, etc., which is not present here. This is actually much, much simpler. So the problem setting is to find and navigate to a given goal landmark provided by an image using only onboard camera observations. So you have your initial observation. This is what the robot sees now. You have a goal that is provided by the user, and the robot is supposed to navigate to that goal. And it's supposed to do this in a wide range of diverse environments. So here are some overhead satellite images of these particular trajectories. The satellite images are not actually available to the robot. They're just shown for your visualization. So these are paths that are tens to low hundreds of meters in length, although we could probably go longer. And I'm going to discuss how, in the context of this application, we can have reinforcement learning algorithms that can use broad and diverse data sets. Hopefully it's obvious why that's needed because we need to navigate in all these diverse settings. But I'll also talk about how we can leverage this starting point to rapidly adapt to new tasks. Just like that home robot needed to adapt to your particular bathroom, I'll talk about how these navigational systems can adapt to a particular environment, quickly explore it to find unknown goals, and then visit other goals in that same environment very rapidly by using a kind of mental map that they construct. But let's start with part one. So since we need to deal with camera observations and goal images, we're going to train a model on a large repertoire of navigational data, and that model is going to work like this. It'll take in a starting observation, the current thing the robot sees, and it will take in a goal, and it will featureize both of them using confidence. And then it will combine those featurizations, and from the embedding of the current observation and the goal, it'll predict two things. It'll predict the number of time steps that are necessary to transit between the current observation and the goal, and it'll predict the current action it should take to get there. Okay, now of course the obvious question you'd ask is, well, how do we actually train this model? So the way we're going to train this model is by collecting a data set of random navigation. So we'll just have the robot drive around in a variety of different environments and collect data. And then we'll simply take out the subsequences in that data set. So if you saw a particular image and then 5 steps later you saw another image, that is a training example you can use where the distance label is 5 and the action label is the action you took. In reality, you can do something a bit more sophisticated. You can actually use Q-learning algorithms, in which case the distance plays the role of the value function and the action plays the role of the policy. And both choices are actually reasonable. Once you've built up this kind of model, it can serve as essentially a short horizon navigational skill. But what we actually want to perform here are long horizon navigational skills. So the model itself is not good enough. What we actually need to do is we need to construct a kind of mental map in each environment that we navigate. And we construct that mental map out of the particular images the robot saw in that particular environment. If you're in a known environment, an environment that was present in the training set, this is quite easy. If you're in a new environment that you haven't seen before, this is a bit harder, and I'll describe in a second how that would work. But for now, let's just say we're in a known environment. So in that case, we have some observations, and we can use those observations to build a graph. The nodes in the graph are images that we've seen. The edges in the graph have weights given by the distance predicted by our model. Okay, now of course, this might resemble the kind of approaches we would take in SLAM and conventional planning, but remember the graph is not actually spatial. It's visualized spatially here just for your reference, but as far as the robot is concerned, it's just a graph where images, first-person images, are connected by edges. There's no attempt to reconstruct the geometry of the environment. Now, this idea by itself is not actually new to this paper. It was previously proposed in several papers, such as SPTM and SORB, but here it's being used in this offline setting where we're actually using large amounts of prior data to train this model and use it to navigate real-world environments. So from a systems standpoint, a particularly interesting detail, at least to me in this approach, is that all 40 hours of training data that was used to train this model were collected offline, meaning that they were not actually collected with the robot trying to navigate to goals. In fact, they were collected for a completely different project. They were collected for a project led by my student Gregory Kahn called Badger, which was concerned with a somewhat different problem. And the data was collected actually 4 months prior to when Dhruv carried out this work. So he simply took that data set that was collected in the spring, and then he carried out these experiments actually in the fall of 2020 without actually any additional data collection. Just took the data, used it to train the model, and then directly applied that model to generalize to this wide range of environments. And this illustrates the power of offline training. If you can reuse your data sets, you can have these large data sets and use them again and again. So here is this method in action. And Dhruv put together a few kind of simple demos that illustrate some of the things you could do with this idea. Here is a little pizza delivery application. So you take a photo of your front door, and you don't, because of the pandemic, you don't want to actually deliver it by hand, so you have the robot do it, okay? Autonomous inspection. Take a series of photographs of waypoints that you would like the robot to patrol, and then the robot will autonomously navigate between those waypoints. There is no explicit SLAM, localization, geometry. All that the robot has to go on is this mental map, this topological graph that it constructed from its previous experience in this environment. Okay, so how about exploring new environments? And that's the bit that I really want to focus on for this application. How can we leverage the starting point to rapidly adapt to new tasks? If you're placed in a new environment, maybe you need to deliver packages on my street here in Berkeley, and you've never been in this part of the city before, what do? So you have some training environments and you have new test environments. Well, the obvious problem is your current observation that you're seeing right now might not tell you anything about where the goal is. So let's say I need to deliver a package to this front door, and the image in the bottom left is what the robot is seeing now. Okay, what should it do? There's no way to know. Well, what would a person do? We have all sorts of navigational priors. If I tell you to deliver a package and I give you a photograph of someone's front door, and you're currently in the middle of the street, well, you could drive down the street, look left, look right, look at the different front doors that are there until you find the right one. What you probably won't do is you won't drive into the bushes and go into a ravine, because you know that front doors don't tend to be in bushes or ravines. So you will use your navigational common sense. And here's that theme again. Common sense, where does it come from? It comes from data. And that's where we're going to get our navigational skills. So what we're going to do is we're going to augment the method from the previous project to allow it to explore new environments. And it will explore new environments by proposing latent goals. It will actually imagine the kinds of goals it could reach in these environments, attempt to reach them, and build out its mental map right on the fly. And it will do this in a matter of minutes. So our model is going to look very similar to the model we had before, with some modifications. We'll again have a convnet that encodes the current observation and the goal. But now the goal observation will be bottlenecked through a latent variable. So this is a latent goal variable. You can think of it as a kind of random variable representation of goals. It's not an image. It contains only the information necessary to decide how to navigate to that goal and predict the distance necessary to reach it. So it'll discard irrelevant distractors like time of day or weather. You take a photograph of your front door at night, it should have the same representation during the day, because that does not affect the navigational skill. We implement this random variable with a variational information bottleneck, which allows us to put a prior on that variable. So the prior is P0 of z, which is a zero mean unit variance Gaussian, and there's a posterior, P of z given s comma g. So that's the posterior over z given their current observation and goal. And you can sample these goals from a prior, and that will give you essentially random navigational goals, or you can sample it from the posterior, which will ask the model how to navigate to the particular goal image that was given. And then, based on your current observation and this zg variable, you will again predict the distance and the action. Okay, why are we going through these contortions? Well, because we're going to use the ability to sample goals, as well as the ability to assign a probability to a goal, in order to rapidly explore a new environment and build out this mental map, to essentially search for a destination. And this is very much like the bathroom cleaning from before, although of course mechanically a lot simpler. In the same way that that home robot needed to master your particular bathroom in order to clean it well, this navigational robot will need to master its new environment in order to build out that mental map and reach destinations in that mental map. And everything is still going to be trained on the same exact offline data set, that same 40 hours of experience that we used to train the previous model. So there's no additional data collection for this. We're just using the data in a different way. There will, of course, be additional data collection in the new environment, but that'll be very fast. That'll be on the order of tens of minutes. So first, a little unit test. Here we place the robot in a courtyard. This is at Richmond Field Station, north of UC Berkeley. And we initially ran a baseline where we had it explore by taking random actions. And you can see the robot explored a region with a diameter of about 7 or 8 meters. We then had it explore by sampling random goals, random ZGs from the prior. And at that point, the robot actually covered a region that was about 15 to 18 meters in diameter, much larger than it did with random actions. So sampling random goals really works. It picks random valid destinations in the current environment where the robot is at. And remember, these goals are not images. They're actually latent representations. They discard everything that is irrelevant to navigation. So here's the full search application. In the first run, the robot has never seen this environment before. And what we're going to do is we're going to give it a goal image, and then we'll let it explore. Now, of course, it doesn't know where this doorway is, so what it's doing when it explores is it's building its mental map on the fly, and at each point in time, it selects a goal. The way that it chooses its goals is following. If the current posterior for the true task goal assigns a high probability, then it will navigate to the task goal. What that means is that when it sees, let me just play it again, when it sees the task goal, it will navigate to it. Basically, when it's confident that the task goal is in distribution, it'll just go to the task goal. If the probability assigned to the task goal is low, what it will do is it'll attempt to reach the frontier of the current mental map. The frontier is the part of the mental map that has a low visitation count. If it's already on the frontier, then it will sample a random goal. So the practical effect of this is that it tries to broaden the region of the current environment that it's explored until it catches sight of the task goal, at which point it navigates to it, and that's what you can see here. So what I want to draw your attention to at the end here is the actual map of the environment. So we can see the map right there. So the blue trajectory here indicates the actual path the robot took while searching for the goal. The red trajectory is what it then did to revisit the goal after the initial search was complete. So once it performs that search, it builds a mental map and then it can visit the goal very, very rapidly. And you can see that in part 2 of the video, which I can play right there. So after exploration is done, it builds the map, and then it can navigate to the goal again, or other goals in that same environment, in just a few seconds. So it took 20 minutes to build the map, and then to navigate to the goal again, it requires just 20 seconds, and that's what you're going to see here for run 2. Okay, there it goes. So it pretty much takes a direct path right down the road and goes to the goal. All right, now let's talk about the third ingredient, trying again. So I mentioned that we need the robotic systems that can do all this autonomously, and this was fairly straightforward to do in the navigational setting because you don't have to deal with spilled water buckets in the navigational setting. But what about more complex situations? How can we have robots that adapt to tasks without human intervention? Let's think of an example. Let's say that you have a robot that is supposed to make some coffee with a coffee machine, a robot barista. So it picks up a cup and puts it in the coffee machine. Well, you can imagine that it has a task. Let's call it task 1, put cup in coffee machine. And it fails at that task. Maybe it knocks the cup over because it doesn't yet know how to pick up this cup. It has some weird handle, something like that. Well, a person could come in and reset the cup and it can try again. But that's no good. You can't have a robot practice this task while you're away at work. So you'd like to not require any intervention. You'd like it to do all this autonomously. Well, what if you have a second task? What if you have a second task called pick up the cup? So then if the robot drop the cup, that's an opportunity. It's an opportunity to practice another task. And maybe once it succeeds at the picking up task, it can try putting the cup in the coffee machine again. And maybe it succeeds at that, and then the next task is to replace the cup, take it back out of the coffee machine so that it can retry. And maybe it spills the cup. At that point, perhaps it's an opportunity for it to practice cleaning the spill. and so forth. The point is that having a multitask setting can enable robots to practice tasks autonomously. It might seem a little contradictory at first. You would think that learning one task at a time would be easier, but if you learn multiple tasks, those tasks can reset each other, enabling the whole system to be much more autonomous. It turns out that actually practicing multiple tasks at the same time has many other benefits, but for now let's focus on the benefit of autonomy. The task we're going to do is here is going to be a little different. This is a paper led by my student Abhishek Gupta called Reset-Free Reinforcement Learning via Multitask Learning, Learning Dexterous Manipulation Behaviors Without Human Intervention. And the task we want is for a robotic hand, this is a four-finger hand mounted at the end of an arm, to reorient an object in the palm. So it's supposed to pick up this object and position it in a particular location, a particular orientation in the palm. So it has to pick it up, flip it over, and then it has to do this kind of cool in-hand manipulation to move it around so that it sits firmly in the palm at the desired location. So it's going to reorient it. There it goes. Okay. So it has to do a little bit of a fine-grained finger manipulation to really get it there. What we're going to try to do is learn this task entirely in the real world without any human intervention. The same way that that bathroom cleaning robot would practice cleaning the bathroom while you're away at work. And to do this, we won't have just one task, we'll actually have many tasks. Because the robot could drop this object, it might need to reposition it, so we actually will build a task graph. This is a graph where nodes are tasks and edges are which tasks can lead to which other tasks. So if you want to pick up the object, you need to first recenter it in the bin, then you lift it up. If you lift it up, you can flip it over. If it's in your hand, you can reposition it in the hand, or you can drop it to practice lifting again. So if you can build this kind of graph of tasks and then learn all the tasks together, selecting which tasks to practice at any given time by using the graph, the whole thing can actually be learned autonomously. So what I'm going to show you next is actually the entire training process. I can show you the entire training process because it doesn't require human intervention. It takes several days to learn this. This is a complex task. It requires using a multi-fingered hand, very complex contexts. It is entirely learned, entirely end-to-end, and entirely without human intervention. And that's why we put the clock there so you can see it. Now I wanted to get this video down to about 30 seconds, so I do crop out some parts, but it just keeps going like this, and it keeps going for several days. And by the time it is finished, then it can perform this task pretty reliably. So the point here is that multitask learning can enable learning tasks fully autonomously and adapting them fully autonomously, just like that bathroom cleaning robot. Here's another task that we can do with this method. Here the goal is to pick up this connector and connect it to the peg in the wall here. Now here the robot actually failed on the first grasp attempt, but it's okay, you can just try again. And then it can reposition it and plug the connector into the socket. Now of course the socket is pretty loose, so there's some details here that we need to get right, and of course there's much more room for improvement. But nonetheless, this kind of fairly complex task can be performed using a robotic arm with a four-finger hand, lots of complex contact dynamics, and lots of complex object manipulation. So the main idea here is that learning multiple tasks simultaneously can allow robots to learn entirely autonomously in the real world. All right, so that takes care of number 1, number 2, and number 3. To conclude, I want to tell you about a couple other projects that really try to take some of these basic principles and apply them at larger scale. Because if we really do want to move towards the kind of generalist robots that can clean your bathroom and do all the other chores around the house, as well as all the other complex tasks we might want robotic systems to perform in the real world, we're going to need to scale these things up. We've been working on this problem quite a lot actually at Google. In 2018, we had this work called QT-Opt. QT-Opt was essentially a large-scale robotic learning system that could use large amounts of data, combined with both offline and online training, to learn a very general robotic task, which was picking up objects. The setup for QT-Opt was that it was trained on about 1,000 training objects, with about 600,000 training grasp attempts. So this is a very large-scale robotic learning system. It would perform these tasks entirely using RGB images from an over-the-shoulder camera, shown in the top left. And it would train a Q function network with about 1.2 million parameters, which is very small by computer vision standards, but it's huge by robotics and deep RL standards. Importantly, and this detail will become very important later, the only grasp-specific feature in the system is the reward function, which was 1 if an object was grasped. Everything else was general and could be applied to other manipulation skills. Now, back in 2018, we evaluated the system for grasping, and we found that it performed very well, but more than just performing really well, it exhibited really interesting behaviors that are pretty unusual in a robotic grasping system. Typically, robotic grasping is framed as a kind of geometry problem. Move towards an object and position the gripper in the right grasp position. Whereas the QT-opt system was reactive. It would treat grasping as a closed-loop control problem, which means that it would react to changes in the environment. If it failed to pick up an object properly, it would reposition the fingers and try again. It would perform pre-grasp manipulations, singulating objects, and it would do all this entirely automatically. It didn't need to be told that these behaviors were necessary. And that enabled it to pick up small objects, large objects, transparent objects, objects that were deformable. In fact, in a test set containing a wide range of fairly difficult test objects, it had a success rate of 96%, which to my knowledge is the best reported result for grasping from RGB images without any depth sensing. More recently, and this is the main thing that I want to focus on in this part of the talk, we've extended this system to perform a wide range of tasks. And we've actually found that multitask learning can be tremendously beneficial, not just for automating the learning process, but actually for attaining the best success rates. And we call the system MT-opt because it can perform many different tasks. So the idea in MT-opt is to set up a similar kind of multi-robot training setup where the robots are now performing a wide range of different tasks. Crucially, the data is shared across these tasks, as are the neural network parameters. And the reason this is so important is because while attempting one task, the robots might actually succeed or collect relevant data for another task. And with an appropriate choice of data sharing strategy, data across tasks can be relabeled and reused for a wide range of other tasks, which can substantially improve success rates, especially for those tasks that are more difficult or more underrepresented in the data set. So this approach generalizes QT-opt to learn multitask policies. There are 12 training tasks, and our experiments here actually show that sharing data improves performance on all the tasks and allows rapidly fine-tuning to new tasks. Now, there are a few details we have to get right to make this possible. For example, since we're going to have so many tasks, we need a scalable way to define task rewards. Instead of coding up rewards manually, we actually define rewards with classifiers that can be trained on data collected by non-expert users. There are 12 tasks used for training that involve repositioning objects in various ways, and then the system can be applied to a wide range of other tasks at test time, like placing noodles in a bowl and things like that. Empirically, one of the interesting conclusions from this work is that this sort of multitask learning, where data and model features are shared across tasks, can be extremely beneficial, particularly for those tasks that are underrepresented. So here you can see the 12 training tasks, and for each one, the green bar represents the performance of MT-opt, the beige bar represents regular single task QT-opt, and blue and red show ablations of various data sharing strategies. All tasks are trained jointly, and they're actually trained entirely with offline RL. So the data for this was, again, collected over several months. It required a very large amount of data, and these results are from policy trained offline on all of that data. Now, what I'm showing you here on the right is the number of episodes by task type. Now, of course, the lift any task that's just regular grasping was wildly overrepresented in the data set because basically anything that the robot does involves lifting something. Many of the other tasks were very underrepresented. For example, some of the semantic picking tasks, lift banana, lift bottle, etc., have a very small number of episodes by comparison. And those are exactly the tasks that show the largest improvement between MT-opt and all the baselines. So it's exactly those tasks that are the most underrepresented that are improved the most by data sharing and sharing representations. Now, this may be a somewhat obvious conclusion. In fact, it's what a lot of people suspect is true for multitask learning, but this work actually demonstrates that in a very large-scale, real-world robotic system. And sharing data from all the past tasks massively improves performance here. So this is very much getting at the point that I made in the beginning of the talk, where we can use large data sets from past interactions. We can, of course, also fine-tune these very rapidly to new tasks. Here's an example of how the data sharing works. Let's say the robot performed this behavior during training. It picked up the soup bowl and dropped it in the plate. That's a success for picking up any object. It's a success for picking up the can, and it's also a success for placing any object, as well as placing any object in the lower small compartment of a green plate. So that single episode is useful for many things. And we can use these learn multitask policies to then perform other tasks like lifting up this towel, which were not actually seen in the training data. And later on, the robot would actually place the towel over the block. So we can perform a wide range of different tasks with the system. So this is just showing kind of a montage of different behaviors that the system mastered, from placing objects into bags here in the bottom center, moving bottles into containers, stuff like that. So there's all sorts of things that this approach can actually do. But can we go even further? Can we also automate the process of task specification? Well, one of the things that we've done, and this is another paper led by Yevgen Chebatar called Actionable Models, is apply a similar principle that we saw in the navigation domain before, where we actually condition the policy on a representation of the goal. In this case, it's also going to be a goal image. So here there's no reward function at all. The task is defined entirely using a goal image that is given to the robot. But in this manipulation setting, using the same exact data that we used for the MT-opt project. So just like in the navigation setting, we have a goal image, and the robot's task is to reconfigure the environment so that it matches this goal image. This is going to use a conservative offline RL method designed for goal reaching based on a variant of conservative Q-learning, and it's going to use the same exact data as MT-opt. In fact, we didn't collect any new data for this project whatsoever. The only thing we did with real robots here is just the evaluation. And you can perform a wide range of different tasks now without any reward specification at all, just by using these goal images. You could, for example, give an image of the robot holding a bottle, and we'll figure out how to pick up a bottle. You could give the robot an image of holding a carrot, and it'll pick up a carrot. You could give it a goal image where it's holding the corn, and it'll pick up the corn. And you can also ask it to perform, besides these grasping tasks, some rearrangement tasks. So, for example, we could specify a task like moving the banana into the green bowl. So the goal image has the banana in the green bowl, and it'll figure out that what it needs to do is pick up the banana and drop it in the green bowl. Here, the broccoli has been added to the bowl in the goal image, and it figures out that it needs to pick up the broccoli and put it in the bowl. Here, in the goal image, the banana is next to the carrot. It takes a few tries to reposition it properly, but eventually gets pretty close to the desired location. Here, the carrot is moved away from the tomato, and one of the really interesting things about the system is because it really is a closed-loop system, it's going to fiddle with this carrot quite a few times and get it very close to the right location. Now, of course, specifying these goal images to define every single manipulation task can be a little bit onerous. But one of the really interesting things we can do with this kind of approach is essentially use it as a kind of unsupervised pre-training for RL. So, as many of you probably know, unsupervised pre-training has been tremendously successful in domains from NLP to computer vision, where we train up models on large, diverse data sets, often with unsupervised objectives, and then fine-tune them with a modest amount of data for a particular task. So we can do this with actionable models. We can train a goal condition Q function with offline RL, and then fine-tune it with a task reward with a limited amount of data. In the actual experiments, another very similar thing we can do is actually joint training. So instead of just pre-training, we can have two heads, and we can keep running the goal reaching data through the model as well to make sure it doesn't forget it. So we have one head for goal conditioned offline RL, and another one for task-specific learning for a given task reward. And that's shown in blue here. And you can see that it significantly accelerates acquisition of these tasks that are defined now with regular rewards. So the orange curve is the baseline that just uses the task reward. The blue curve includes actionable models, and it is much more efficient. All right, so where do we go from here? I talked about how we need these three things. We need reinforcement learning algorithms that can use broad and diverse data sets. We need to leverage the starting point to rapidly adapt to new tasks. And we need to do all of this fully autonomously in real-world settings. So we saw how handling broad and diverse data sets can give robots a notion of common sense, how adapting to new tasks can be accelerated by leveraging prior data and then appropriately using latent variable models, how multitask setups can allow for fully autonomous real-world training, and if we scale all this up, we can actually get meaningful generalization across a wide range of different tasks. So what else do we need? Well, there are a number of components that we've also been developing, although there's still a lot of room for improvement, that I did not discuss in this talk. For example, one of them is algorithms. We need effective algorithms for this offline reinforcement learning. I didn't tell you how those algorithms work, but a few references if you're interested in In this CQL, which was used in a number of the results I presented, conservative Q-learning, that's a method for offline RM, as well as Awake, which is a very effective method for using offline data with some online fine-tuning. We need algorithms for meta-learning and for learning to explore so that we can fine-tune from additional interaction very rapidly. And we saw how latent variables can be useful for that. There is a meta-learning method that we've developed that also uses latent variables called Perl. And if you're interested in learning how to rapidly explore from demonstration data from humans, you can check out this paper called Parrot. And also to enable all this, we need effective data sets for robotic learning. Hopefully, you saw that in a lot of the projects that I described, there are multiple different methods that reuse the same data. In the navigational setting, we use that same 40 hours of training data to perform multiple tasks. In the MTOP project, we collected a data set and then we were able to use that data set for multiple different experiments. Sharing data sets in robotics, I think, is tremendously important. We've taken some steps towards that by developing a data set called RoboNet, which is a large-scale multi-robot data set. But I think we really need to move much more towards sharing data sets and data set-driven research culture in robotics to actually start getting at generalization. But perhaps more broadly, the message I want to leave you with is that addressing these challenges will bring us closer to truly in-the-wild robotic systems that can generalize broadly, perform diverse tasks, and autonomously improve their performance without human involvement. We're still a long ways away from that final goal. I hope that some of the methods that I described today might serve as starting points in this direction, but if you're interested in this topic of research, there's a lot left to do, and I strongly encourage you to think about how you can tackle some of these problems. And lastly, to conclude, I really do want to make sure to thank all the students and collaborators that were involved in this work, both at UC Berkeley and at Google.